Now we are into our last topic in chapter 7. Okay, still FIR design, but now we are going to talk about the general topic of treating FIR design problem as an optimization problem. 最佳化的问题 optimization problem. So this topic is our optimal FIR filter design. Optimal FIR filter design. And for the sake of discussion in class, we will focus on type 1 low-pass filter design. Okay, so we're going to take the type 1 low-pass filter design as an example. That's what we're going to concentrate on for this meeting today and probably on Thursday. And probably on next Tuesday. This is a kind of a challenging problem to look at. Okay? So now type 1 filter, let's say type 1 zero phase. So in the following discussion, I'm going to assume that we don't mind for the filter to have non-zero samples in the negative time. Okay? But that is really, we're going to assume that here we're going to give us a constraint first. Okay, we're going to restrict ourselves to our interest to any filter that satisfies this relation from minus L to L. Okay, so this is our constraint. We're going to restrict our interest to any filter that satisfies this symmetry. And this letter E stands for even symmetry. Okay? And FIR, okay, finitely supported from minus L to L. Everywhere else for none. So that means H of n is 0 outside this range, or L, or no. For any n greater than L, we're going to make this constraint that it's 0 also. It only has a middle part from minus L to L. Okay? But we're going to first make this constraint. So that's kind of second assumption. We're going to design a low-pass filter again. Okay? But the first thing we assume let's assume that our result will be, this is the only form that we're interested in. A evenly symmetric filter, zero-phase filter, around time 0. Okay? So therefore, we have talked about its impulse, this frequency response. As a consequence of this symmetry here, we know that in the frequency domain, the frequency response is going to be what? It's going to be real, right? It's going to be real. So we say the frequency response here is going to be real. Why? Because the frequency response here is going to be, according to the definition of DTFT, take it slowly, h e of n, e to the minus j omega n, the same old definition of DTFT, right? I've shown it that it should be real because the result, because of that symmetry, the result is going to be equal to the term at time 0 plus 2 times, because of symmetry there's a factor 2 here, and now we're going to run the time index from 1 to L. And here we have HE of n. And cosine omega n. Because e to the j omega n plus e to the minus j omega n is 2 times cosine omega n. Okay? I hope this looks kind of familiar to you. the frequency response of any filter that satisfies this constraint is going to be real. That frequency response, the corresponding frequency response is going to be real, right? Okay, so far so good. It's going to be real, and the next thing is kind of strange. I'm going to introduce this Chebyshev polynomial. The Chebyshev polynomial. So let's introduce this idea. We are going to introduce this idea called Chebyshev polynomial. So the result of this polynomial, the definition, the nth order Chebyshev polynomial as a function of x is defined as, this is kind of strange, the first one, cosine of n times r cosine x. And this goes by the name Chebyshev polynomial. Must be Russian, Chebyshev. You see it Russian? You see Russian? Maybe Ukrainian or Georgian, I'm not sure. Chebyshev. You can assume it's an East European scholar. Chebyshev polynomial. Okay, so I said this is a bit strange. So this function is defined as cosine n r cosine x. Of course, now here we require x to be in between -1 and 1. Otherwise, r cosine is going to be tricky. Okay, so this is a function defined over the closed interval -1 to 1. Okay, I claim that this is actually a polynomial. So then you see that. It is kind of surprising. And cosine of n r cosine x is a polynomial of x. It can look a bit strange, but let me say this, you'll just say, oh, now it makes a lot of sense. In other words, okay, if we define this t of x as such, then we know that t of, if we plug in x equal to cosine omega, okay? So this is really, if t of x is defined like that, then t of cosine omega is going to be cosine of, and r cosine of omega is cosine n omega, right? Is that clear enough? But for example, it becomes clearer. Let's say, for example, cosine 2 omega. Cosine 2 omega is 2 cosine square omega minus 1, right? So therefore, in other words, we say, okay, this t2 of x, the second order Chebyshev polynomial is simply 2x squared minus 1. That's the idea. It's actually not that hard to understand. Let's keep on. So this is not clear yet. Clear enough. So how about cosine 3 omega? Cosine 3 omega relates to cosine omega by some kind of formula, right? They told me. What is cosine 3 omega? Cosine 3 omega is 3 cosine omega minus 4 cosine omega to the third power. So that is, we say t3 of x is 3x minus 4 times x to the third power cubed. And so on and so forth, okay? So you can imagine that in general, cosine n omega has this formula. Cosine, you can always express cosine n times omega n being an integer. Okay? Here, let me say just natural number. Okay? Cosine n, you can always express cosine n omega in terms of cosine omega, and that relation gives you the corresponding Chebyshev polynomial. So if for example, if cosine 2 omega is this, then t2x is 2 times x squared minus 1. So that's the relation. Okay? So in general, t n x would be an nth order polynomial. T n x if you actually borrow notation from linear algebra, ENX is an nth order polynomial of x. Okay, nth order polynomial of x. Okay. So now I'm going to move on to show how we can formulate. So today we're not going to design the filter, but at least we can formulate the filter design problem as an optimization problem. And in doing that, we need some help from Chebyshev polynomial. There's the reason why we mentioned Chebyshev polynomial right here. So first of all, let's kind of simplify our notation. So here, I'm going to call the frequency response. So let's define, okay, I don't absolutely have to do that, but yeah. Let me say H, this frequency response, which is 2 times plus 2 times from 1 to L cosine omega n. But now cosine omega n is what? Is Chebyshev polynomial. Is a Chebyshev polynomial taken at x equals to cosine omega. Okay? So here we can say, still copying everything, and 2 times n from 1 to L, here still this. Cosine n times omega is going to be t of cosine omega, right? You know we can do that. We can expand cosine n times the frequency into a polynomial of cosine omega. And this, so we are going to call this as, so if we just expand everything here, the result at n runs from 1, 2, 3, 4, 5 all the way to L. L being kind of the length. Let's describe the length of our filter, half length of the filter. Okay? So if we just keep going and let n runs from 1 to L, the result is going to be a big polynomial of cosine omega. Because everything here is a polynomial, right? And we sum them up, the finite sum, the result of the summation is also going to be a polynomial. Can we agree on that? So I'm going to just roughly say the result is going to be a polynomial in terms of ak cosine omega to the k power. Here, k runs from 0 to all the way to L, L being the highest order. Okay? So that is to say, if we are given the H, these samples, H0, H1, H2, all the way to HL, the negative time has an even symmetry to the positive sign. Okay? So if we're given all the samples, then we can calculate the coefficients right here by expanding the Chebyshev polynomial. In principle, we can do that. What might be tougher is how do you, it's actually not that tough. So you can imagine this is a linear mapping. So by solving a system equation using Gaussian elimination, you can just do the reverse. Okay, we say that even any AK, all the coefficients A1, A0, A1, A2 to L. Given all the L plus 1 coefficients here, we can also back calculate the corresponding samples in the time domain. So let me just can we agree on that? So there is a one-to-one correspondence. So note that there is a one-to-one correspondence. Okay. one-to-one correspondence between the set of samples n from 0 to L and the set of these A coefficients k from 0 to L. There's a linear mapping between these two things. Given that as long as you know how to calculate the Chebyshev polynomial. Okay. Given that you know exactly how to expand cosine n omega n being any integer. That might be the tough one. Okay. Can you tell me what's the formula for cosine 11 omega? Not my part. What's the formula for cosine 7 omega? Sorry, nobody could memorize that. But you can either find it in the internet. Actually, there's also a systematic way to calculate that. Okay, so I'll just my one. But if we can really calculate Chebyshev polynomial, let's agree on that. We can we can calculate A from H and also calculate H from A. There's a one-to-one correspondence between the coefficients A and the sample values H. Any questions so far? So far so good? Not so good? Okay, so further, I'm going to just be lazy. Let's rewrite this the result of our design as the frequency response as simply A of omega, and to save our effort later. Okay, just a shorthand. Just being lazy. Let me just call this thing A of omega. The frequency, which is the frequency response of some kind of system. Some kind of evenly symmetric zero-phase filter. And this is the frequency response. So now back to filter design. Okay, so that leads us back to filter design. Let's say if still we always have a kind of desired response in mind. Let's say when we design low pass filter, now we're given the specification, right? Usually we're given the specification of what is the cutoff frequency, the height frequency for pass band, and the starting frequency for stop band. After that, so after beyond stop frequency, the ideal response should be 0, and in this frequency band, the ideal response should be 1. So let's call this the desired response. I'm going to be lazy again here. The desired response is simply defined like that over a few closed intervals. So let's say explicitly the desire. D stands for design. Design. 想要的 design. The desired response is 1 for omega belongs to 0 all the way to the edge of the path end. And the desired response is 0 when omega is between the edge frequency for the stop band all the way to pi. So it's defined over two disjoint closed intervals. How about the transition region? How about transition region? The kind of nice thing about this way of thinking. I'm going to tell you, it turns out that you'll see the transition region is going to be treated as a kind of don't care region. This is kind of strange, okay? So we are going to not care about whatever happens, okay? So here, I say don't care. That kind of spirit of optimal design. Let me just share with you first that you'll see that in the end, we define the transition input. So the question is, so we don't care. E equals to don't care if omega is in between. It's between the edge of the path band and the starting to the stop band. Don't care. Okay? But then, given this nice kind of requirement, don't care in this. So don't care in this. If we don't care, how do we describe we don't care? Well, how do we describe mathematically we don't care about something? So turns out we need to define a loss function and an objective function, and in there you will see how to define don't care. Okay? So here I'm going to propose that we're going to come up with a kind of penalty function, okay? So in this optimal, the kind of framework of optimal design, we come up with, we accompany our desired response with a penalty function that is also defined over frequency. So this is a weighting function, so to speak, is W of omega. And by the way, I was grading your exams. Please, after you take this PSP, you should be able to distinguish what is omega and what is W. Okay? It's rounded is omega, and it's sharp is W. Usually, I don't want to see, as a jet, you want you need to separate omega and W. But here, I mean W of omega, because W stands for weight. This penalty function, I call it penalty 处罚, 惩罚, penalty, 知道吗？惩罚啊。We're going to penalize any deviation from ideal. Okay, but how severely you're going to penalize any deviation is described in this W function. Okay, it's a function of omega, and I'm going to define, for example, this is a weighting function we'll see later. Okay, so you can define some kind of penalty for the path n. So let's say the penalty is 1 for path n. And the penalty is larger, a bit larger in this case. The penalty factor is a bit higher, let's say that this factor becomes k, okay, for the stop n. And the penalty, you can define it to be 0. That's the way we show that we don't care. Okay? So let's define the penalty to be 0 in the transition region. So this is the way we describe we don't care. There's no penalty. And so from the penalty function, now then we propose to define. From this penalty function, now we propose to define a cost function, E of omega. E of omega, the cost function, or objective function, is defined as this penalty function times the error. Error being h, the desired response minus the result of our design. Right? So that gives us the definition of a cost function. And to finish our formulation, this is a cost function. Okay, the cost function is penalty times any deviation. And in what follows is that we are going to formulate filter design as an optimization function. That is to say, we will find the best. We want to find the best combination of samples. We want to find the best combination of samples which minimizes the maximum cost. Let me say that again. So, as an optimization problem, how do we formulate design as an optimization problem? Now we have a cost function. Okay. Now what we're going to talk next is that we are going to find the goal, the target, the objective is to find the set of samples such that this cost function is minimized in a certain way. Okay, so let me, the formulation, now the goal. Now the goal becomes, we want to find h, the sample values, n, from 0 to L, such that the maximum error is minimized. We want to somehow find the set of samples. And this is designing to find something. This is the result of our design. So we want to find the samples, and there are totally L plus 1 of them. Okay, L plus 1 of them. So these, if you will, you can think of it as a vector in a L+1 dimensional space. Okay, so we want to find a vector of L+1 in the L+1 dimensional space such that the maximum error with respect to omega, so throughout the whole frequency range, such that the maximum error is minimized. In other words, this is what they call a min-max problem, min-max problem, minimizing the maximum error. Okay, minimizing the maximum error. Or more fancier, let's define this. If we say, okay, this is a vector. This is a kind of preferred way I was thinking of. So if we define the set of all samples as something, some kind of a vector in the L+1 dimensional space, okay? So our problem description is that we want to find HL, or should I say, we want to find H, the optimal design, okay? The optimal design is the design which the argument in the L+1 dimensional space such that the maximum error is minimized. So that's our problem, our kind of description of our goal. We want to find the argument 就是函数，把什么东西放到函数里面的东西叫 argument. Argument is the stuff, the object that you send to your function. Okay, so we want to find the argument such that the maximum cost is minimized. That's the problem formulation. Okay, that's the problem formulation. So once somehow we can find such H, suppose that we are so fortunate that we know how to find this H. But now it becomes a optimality function, a search of all possible vectors in the L+1 dimensional space. How to search that is the next topic. But in general, this is an optimization. I hope you can get a feeling how come this becomes an optimization problem. But here, we're not talking about windowing, we're not talking about IR or anything. Just kind of formally to think about our desired response. We accompany that by a penalty function to describe that we really don't care. Particularly, we really don't care for the transition region, there's no penalty. Okay? But then, when we multiply the deviation and the weighting function here, that's the cost function, and we want to minimize the maximum error across all possible omega. Okay? So the result is to find the argument which minimizes the maximum cost. So once we find this optimal set of samples, this is H hat. Oh no. Once we refine it, we're set. Okay? And so let me kind of just stop here and to kind of give you a preview for Thursday. We continue talking about this. It turns out that it's easier to think not in terms of H, but in terms of those Chebyshev coefficients. It turns out that this Chebyshev polynomial is going to be useful in a way. It turns out that we are going to find, we are not going to find the samples directly, but we are going to find the coefficients. We're going to find the A coefficients. So on Thursday, when we continue our discussion, you'll see that we are going to find these things first. And after we find the optimal coefficients, we kind of translate it into H. Okay, so that's kind of our plan for discussion on Thursday. So please come back for the discussion. Thank you for being here, and see you on Thursday.